Previously in the course, we discussed the process of effusion of gases and how scientists at the Oak Ridge National Laboratory in Tennessee used that technique to obtain enriched uranium-235. But back then we stopped short of asking a deeper question of why. Why was that huge facility at Oak Ridge National Laboratory necessary? What was it about uranium-235 that made it necessary for the construction of the awesome weapon that helped to end World War II? Today we're going to fill in that gap as we look beyond more qualitative characteristics like the zone of stability. Today we're going to put our calculators to this problem and demonstrate why so little nuclear material can pack such tremendous energy that its release can halt a war in its tracks. Matter and energy. For so long, they were so very conveniently divorced in the minds of physicists. At least, that assumption was widely applied. But even as early as 1717, the undisputed father of modern physics, Isaac Newton, questioned that very principle when he considered the possibility that light and matter could be interconverted. For so many years, though, the laws of conservation of mass and conservation of energy held fast in the face of scientific scrutiny. The only way it seemed that energy could be stored and released was in the breaking and making of chemical bonds. Atoms themselves, at least until the days of Becquerel and Rutherford, appeared to truly adhere to inspiration for their name: indestructible, indivisible objects. But that began to change when Becquerel first observed the effects of radiation in his uranium samples. Rutherford and others continued refining our understanding of the structure of the atom and the origins of this radiation until a grand realization was made by one of the greatest physicists of all time, Albert Einstein. In 1905, Einstein published a paper in which he famously shattered the old paradigm that matter and energy were separate. He did this by offering a mathematical relationship that quantified what Newton had suspected almost 200 years earlier. This mathematical relationship is known as his mass-energy relationship, or Einstein's equation. In short, he proved that matter and energy were not separate entities, but could be interconverted. That's right, matter can be turned into energy, and vice versa. His equation was almost mind-bogglingly simple, relating the mass of an object to the energy that it can be converted into by just a single proportionality constant, the square of the speed of light. This equation, E equals mc squared, has become the most iconic physical equation of all time. Not only because it's so easy to remember, but because it represents a fundamental shift in the way that humans look at the universe. Now, that fundamental shift in thinking involved just how much energy can be stored in and retrieved from matter. And to give you an appreciation for exactly how much energy matter can store, let's do a thought experiment using Einstein's equation. We're going to do something here that we never really could accomplish in real life, but let's just ask the question. In 1 gram of matter, how much mass energy is stored? If I could find some way to convert all of that matter into energy, how much energy would I get? Now, to do this, of course, we're going to use Einstein's famous equation, E equals mc squared, where energy is equal to the mass of our sample in kilograms times the speed of light squared in meters per second. And we'll see in a moment why we're using these units. So, let's get busy here. Let's determine the total amount of energy in that 1 gram of matter. I'm going to use, again, kilograms, so I'm careful to make a conversion here. I've gone from 1 gram to 0.001 kilograms. It's an equivalent mass. We'll multiply that times the speed of light squared. And our answer is 9 times 10 to the 13 kilograms meter squared per second squared. Now, those are the fundamental units that define a joule. So our 1 gram of matter, if it were completely converted into energy, would give us 9 times 10 to the 13th joules. But how much energy is that really? Well, let's do another quick calculation. Let's take our joules, convert that into food calories, something that we can all really appreciate. Now, there are 4.18 joules per calorie, But remember, a food calorie is actually 1,000 times an actual calorie. So if we run our calculation, this will give us the total number of food calories contained in that 9 times 10 to the 13 joules that would have come from our gram of matter. And the answer that we get is 2.15 times 10 to the 10th kilocalories. Folks, that is the amount of energy contained in the healthy diet of a human being over 29,500 years or so. That's a pretty impressive amount of energy out of 1 gram of matter. So Einstein's mass-energy relationship gives us not only a way to relate mass to energy, but a new respect for the almost incomprehensible amount of energy that's available to be tapped if we can control that interconversion. You might still be reeling a bit from my most recent assertion that you could extract billions of calories of energy from just 1 gram of matter. It's tough to believe, isn't it? Well, in a sense, it is pretty unbelievable because we have no way of completely converting a sample of matter into energy. That kind of wholesale interchange is simply not achievable under any kind of conditions that we can even imagine, let alone create. So why then was the mass-energy relationship such a big deal? The answer to that question is nuclear chemistry. Einstein's equation doesn't just explain some hopelessly theoretical situation like our thought experiment in the last segment. It also explains a very observable and very useful phenomenon that we see in atoms, a phenomenon known as the mass defect. You may remember J.J. Thomson, the discoverer of the electron and inventor of the cathode ray tube. Thomson is revered for his discovery of the electron, but like most good scientists, he didn't let something like a Nobel Prize slow him down. No, he had more ideas to explore. Now recall that Thomson was able to estimate the mass of an electron by deflecting it in an electrical or magnetic field as it moved through one of his famous cathode ray tubes. That was a brilliant concept, and one that he continued to develop and refine. Thomson used a similar strategy to devise an instrument that could be used to measure the mass of practically anything with a charge. His new creation was called a mass spectrometer, and it worked on principles similar to his cathode ray tube. Just as before, he used an evacuated tube containing a cathode and an anode. But this time, he elongated the tube behind the cathode and found that a positively charged beam was moving in the opposite direction from the cathode rays. He named these positively charged beams canal rays. Thomson placed a photographic plate behind this new positively charged beam and was stunned by what he saw. When an electrostatic or magnetic field was applied across the canal rays, they fanned out into an array of beams, each with a different curvature, all of which were much less than the curvature of the cathode ray. After a bit of calculation, Thomson realized that the various beams in the canal ray were actually cations, positively charged ions, of carbon, oxygen, hydrogen, and other atoms forming in response to the opposing flow of electrons. He named his apparatus a mass spectrometer, and Thomson spent a great deal of his career refining his design in the hopes that his strategy of deflecting canal rays might lead to a technique for determining the mass of atoms and molecules with greater accuracy. True to Thomson's vision, mass spectrometers improved in their precision and accuracy over the years, and soon they yielded the masses of various atoms with truly stunning resolution. Throughout the early 1900s, as mass spectrometry techniques improved and our understanding of atomic structure evolved, scientists began to notice a very interesting trend. Recall that protons and neutrons make up nearly all the mass of an atom. They're collectively called nucleons and are packed together at the nucleus of the atom. So it stands to reason that if we know the mass of a proton and the mass of a neutron, we should be able to calculate the mass of any nucleus simply by accounting for all of the nucleons and adding them up. So let's give that a try right now and see what happens. Let's answer the following question. If a single helium atom is measured to have a mass of 4.00150 atomic mass units, then what is its mass defect? Now, to answer this question, of course, we've got to know the exact mass of a neutron and a proton. Well, we know these numbers. The best resolution mass that I've got, at least, for a proton is this, 1.00728 atomic mass units. And for a neutron, we see something ever so slightly more massive, 1.00866 atomic mass units. So it stands to reason that if I want to know the mass of a helium-4 atom, I can simply add up the appropriate number of protons and neutrons, in this case 2 of each. Right? So my theoretical mass for my alpha particle is simply 2 times the mass of a proton plus 2 times the mass of a neutron, giving me 4.03118 atomic mass units. That sounds pretty simple. However, when the mass of that nucleus is actually measured using a mass spectrometer, we find that it's only 4.00150 atomic mass units. That's too light. And that is the mass defect. Now, the mass defect is simply calculated by taking our theoretical mass and subtracting from it our actual or measured mass. And the balance tells us how much mass is released in the form of energy when we create a helium-4 nucleus from its component nucleons. The answer for here is 0.03038 atomic mass units, a vanishingly small quantity. But as we learned previously, it doesn't take a lot of mass to account for a lot of energy. So let's take that 0.03038 atomic mass units and convert it into, say, kilograms, something that we're more familiar with. We're talking about a mass defect of 5.0449 times 10 to the negative 29th kilograms in one atom. Now, we'll see later why we want to do this in the first place, but this is actually a very, very useful number to have as long as we have Einstein's equation to go along with it. So let's take that mass defect and from it determine the nuclear binding energy, or the total amount of energy that is released when helium-4 is formed from its constituent nucleons. Again, Einstein's equation. The energy is equal to its mass defect, which we calculated previously as 5.0449 times 10 to the negative 29th kilograms. I'll multiply that by the speed of light squared, and I get 4.534 times 10 to the negative 12th kilogram meter square per second square, which we all now know is equal to the same number of joules. So the nuclear binding energy is 4.534 times 10 to the negative 12th joules. But physicists like to use a slightly different unit of energy. Sometimes they use what are called mega electron volts. And in this case, when we do that conversion, you can see why physicists like to use these numbers for nuclear binding energies. Because we get a more manageable number. 28.34 mega electron volts is something that we can compare, right, to other numbers very easily without having to worry about getting lost in the orders of magnitude. Now, if we take that number and acknowledge that there actually are 4 nucleons that come together to form a helium-4 nucleus, we can determine the amount of binding energy per nucleon, which gives us a sort of a normalized value that allows us to compare these types of energies across a range of different atomic sizes. If we want to compare the overall stability of one nucleus or another, however, we can't simply use the overall nuclear binding energy. We have to normalize the binding energy to the total number of nucleons present. Now, when we do this, we notice a very interesting trend in the values that we obtain. This curve of nuclear binding energies, devised by Francis Aston while he was working in J.J. Thomson's laboratory, tells us an amazing story of how and why some of the most powerful energy-emitting processes in the universe take place. It explains so much about what we see in the universe. Notice that binding energy spikes dramatically for helium atoms, explaining why they form so readily, both as the byproduct of our sun's furnace and as alpha particles in radioactive decay, like those we looked at last time. Iron also has a particularly special place. Notice that iron 56 is the king of all nuclei when it comes to binding energy. To separate a nucleus of iron 56 into its constituent parts requires more energy than any other nucleus. And it's this remarkable stability of iron that makes it so common in our universe compared to most other metals. One can very generally say that all nuclei aspire to be iron. So, heavier atoms like uranium and beyond tend to be radioactive, because that process of shedding alpha and beta particles successively can give them a pathway to becoming lighter, more stable elements with a higher nuclear binding energy than the original. Iron-rich meteorites and planetary cores are no accident. They're out there or down there because under the hot, high-pressure conditions of a supernova, iron nuclei form in large amounts, and they're ejected into space as the collapsing star that formed them explodes in a violent supernova. This seeds the universe with the nuclei that it helped to create. So the mass defect is directly proportional to the binding energy holding the nucleus together. But we have no real chance of ever converting an atom completely into energy. As a scientist, I've learned to never say never, but this is something that even a supermassive star cannot accomplish. Even so, both nature and humanity have been able to tap the nuclear binding energy with some amazing results. So let's take a look now at a problem that involves radiation and see if we can explain why alpha particles seem to form so easily from uranium-238. We're going to do this by answering a question, and that question is, using the masses that I'm about to show you, which are measured masses, estimate how much mass energy is released in the alpha decay of the uranium-238 nucleus. Now, this is a process that we looked at last time, so let's review that now, but let's review it in terms of mass defect. Remember, the reaction that we saw was that uranium-238 containing 92 protons and a total of 238 nucleons will decay into an alpha particle, which is a helium nucleus, leaving behind 90 protons to make thorium with a mass of 234. Now, if we measure the actual nuclear masses of these three species, we find that the mass of uranium is 238.05078825 atomic mass units. Thorium is 234.04360123 atomic mass units, and helium is 4.00260325 atomic mass units. These are staggering resolutions, but we need them because we're dealing with such small changes in mass when it comes to mass defect. So how am I going to determine the mass defect of this overall process? Well, I'm going to rely on essentially a version of Hess's law, if you will. I'm going to take my mass balance and say, well, all right, I'm going to take these two species and add them up. That's my mass of my product. I'm going to take this species right here and use that as the mass of my reactant and determine a difference for the reaction. Now, when I do this, right, adding the observed masses of thorium and alpha particles and then subtracting from that the mass of my uranium, what I discover is that the difference here is 0.00458377 atomic mass units. Just a vanishingly small fraction of the mass of a uranium atom. But if a uranium atom is going to undergo this decay, it's obviously going to reach a lower energy state because I found that the delta mass here is actually negative. All right, so let's use that number now and determine what kind of energy we're talking about here. Back to Einstein's equation. Slight variation here. I put delta in front of energy and delta in front of mass, indicating that I'm dealing with the mass defect for a process, comparing one to the other. Right? So this is the total change in mass for the system. That's going to allow me to calculate how the energy of the system changes using my mass defect. So I'll place that into my equation. But I've got an issue here, right? I'm after energy, and I'd like units of joules. Those are my favorites. So to get to joules, I cannot use atomic mass units as my units of mass. Right? That gives me a different unit altogether at the end of the equation. So let's resolve that first by inserting a factor into my equation that's going to cancel atomic mass units and give me kilograms in the numerator of my answer. Next, I'm going to put in my speed of light squared, as usual, 3 times 10 to the 8th meter per second squared. Now, when I run this calculation, what I discover is that I get 6.85 times 10 to the minus 13th joules. Now, let's think about that amount of energy for a moment here. If we use Planck's constant and our now familiar equation that relates the energy in a photon to its wavelength, what type of photon do you think this energy corresponds to? Well, if we run that number, what you're going to find out is that's the energy of a gamma ray photon. So we've not only shown why alpha emission occurs, but we've also succeeded in proving that it should also have a gamma emission associated with it, which is exactly what was observed by Rutherford, Becquerel, and their colleagues. So lowering the per nucleon binding energy is really the driving force behind the radioactivity of uranium and other heavy elements like it. In the face of all this talk about nuclear binding energies and mass defect that occurs when multiple nucleons come together to form a nucleus, you might have asked yourself if chemical bonding creates a similar mass defect. That's a great question. The unfortunate truth is that we simply can't measure any such defect if it exists, even with modern equipment. This is because the energy changes in the breaking of chemical bonds is so very small compared to that of nuclear binding energies. Of course, we already have a sound understanding of how the forming and breaking of chemical bonds releases and absorbs energy. Maybe someday we will have instrumentation so sensitive that we can answer the question of whether or not chemical bonding includes a mass defect. But for now, we simply don't know. It's time to summarize our discussion for this lecture. We started by recounting the work of Isaac Newton and paying particularly close attention to a comment he wrote in 1717, when he wondered if light, the carrier of energy, and matter, the harbinger of mass, might not be able to interconvert with one another somehow. Next, we leapt forward nearly 200 years and had a chat with Albert Einstein, whose mass-energy equation, published in 1905, put a number on that relationship proposed by Newton. We saw how the equation famously links the energy contained in a given mass by the simple constant c squared, or the speed of light squared. We then took a closer look at the atomic nucleus and started to see how measurements made using mass spectrometers were able to confirm that the zone of stability is a very real thing, but that every known spontaneous nuclear decay process is driven by an element's natural tendency to seek out the lower energy state of a more stable nucleus by converting a minuscule but measurable amount of its mass into energy. Finally, we took a look at the idea of mass defect and chemical bonding and considered how the very, very small energy changes involved in chemical bonds would make any mass defect practically impossible for us to measure, if it exists at all. So we've spent 2 lectures considering the atomic nucleus. What makes it stable and what happens when it isn't? How it can often release just a tiny fraction of its nucleus in the form of alpha, beta, or gamma radiations, altering its binding energy and releasing some of its mass defect. But emitting these smaller particles isn't the only pathway for a heavy nucleus to take to a smaller overall mass defect. What happens when atoms don't simply emit a small fraction of their nucleus, but break into 2 large nuclei, effectively releasing a large chunk of it instead? This process is known as nuclear fission, and it's the topic of our next lecture. The elements iron and nickel are remarkably abundant in our cosmos when compared to other metals of similar size. But it's actually not that hard to explain why this phenomenon happens when you think about nuclear binding energies. Let's do that now in a challenge problem. Iron 56 is the most common isotope of iron and has the greatest nuclear binding energy of any element. Now, the mass of this nucleus has been very precisely determined to be 55.920674 atomic mass units. So, using proton and neutron masses that I'm about to give you, try to determine the per nucleon binding energy in mega electron volts for an iron 56 nucleus. Now, here are our masses. We're going to use 1.007277 AMUs as the measured mass of a proton, 1.008665 atomic mass units as the measured mass of a neutron, and 55.920674 AMU as the measured mass of an iron 56 nucleus. I want to be very clear about that. If you go looking for the measured mass of an iron 56 atom, you'll have to remember to subtract the masses of 26 electrons that are in orbit around that nucleus to be sure that your math holds up. Now that we have these numbers, let's start to think about the problem itself. We've got a situation where we want to compare the difference between the energy in an iron 56 nucleus and that of all of the constituent protons and neutrons when they are not contained in a nucleus, but rather are completely separated into individual nucleons. So let's mathematically determine the mass difference, and then we'll use that mass difference to determine the amount of energy change that goes on when we do this thought experiment of ripping an iron atom completely apart into protons and neutrons in isolation from one another. We'll start with the mass of the iron 56 nucleus, given to us in the problem as 55.920674 AMU. Now, 30 neutrons at the mass that I'm given would be equal to 30.259950 AMU. And I'm using very, very precise measurements, really, really long trailing decimals, because I'm expecting a very small mass difference. My 26 protons, I can calculate the mass that I would get from those 26 isolated protons. Here it is, 26.189202 atomic mass units. And the summation of these two numbers gives us the total mass, all the constituent nucleons of an iron 56 nucleus. And as you can see, at 56.449152 atomic mass units, it's considerably heavier, considerably more massive than that iron 56 nucleus was. So we can calculate the difference in mass, of course, simply by subtracting the mass of the intact iron nucleus from the total mass of all the constituent protons and neutrons that made it up. And when we do this, as you can see, it's a fairly small fraction of its mass, but it is a meaningful number. It's 0.528478 atomic mass units. That's the amount of matter that would be converted into energy when we take these protons and neutrons and combine them all into a nucleus in the reverse process in this thought experiment. Now that we've determined the change in mass, or the difference in mass, between our intact nucleus and the separate nucleons that make it up, we're going to use that number to determine the nuclear binding energy, the difference in energy that corresponds to that difference in mass right there, 0.528478 atomic mass units. Now to do that, let's first convert it into kilograms, because ultimately it's easier to get into units of energy when we deal with kilograms, for reasons we'll see in a moment. I'm going to use this factor, 1.66054 times 10 to the negative 27th kilograms per atomic mass unit, which will tell me exactly how many kilograms of mass would be lost if we could build an iron nucleus in this way. And the answer here is 8.77591 times 10 to the minus 28th kilograms worth of mass. Now I'm ready to convert this number into energy. And I'm going to do that using the famous energy-mass relationship, E equals mc squared. In this case, the energy is equal to, again, the change in mass we previously calculated, 8.77591 times 10 to the minus 28th kilograms, times the speed of light squared in meters per second. And this leads to an answer in units of kilograms meters squared per second squared, which is also equal to joules. So the amount of energy, or nuclear binding energy, in this particular nucleus is 7.898319 times 10 to the minus 11th joules. But we're not done answering the question yet. The question asked us about mega electron volts, not joules. So we still have to convert this number from joules into mega electron volts. And we can do this using the conversion factor we saw previously. 1 mega electron volt is equal to 1.602 times 10 to the minus 13th joules. And when we do this, we find that the nuclear binding energy for iron 56 nucleus in mega electron volts is equal to 493. Now, that's the total nuclear binding energy for the entire nucleus, but in order to compare it to other elements, we have to be sure that we break it down to the binding energy per nucleon, which means we want to take that 493.0 mega electron volts and divide through by 56 nucleons in one iron 56 nucleus, and finally we get to our answer, 8.8 mega electron volts per nucleon. This is the highest value that you will find on the per nucleon nuclear binding energy curve.